Uh, Before we get started, as usual, let's recall what we have learned last week. Last week, we mainly talked about the wave mechanics of the atomic model, right? So there are three uh, giants. They are de Broglie, Heisenberg, and Schrödinger. These three giants tell us that electron can behave like a wave as well as a particle, right? That's from de Broglie. And Heisenberg tells us that the uncertainty principle, that means you cannot find the electron, the location of the electron, also the speed of the electron at certain time. Okay, that's the Heisenberg. Schrödinger derived one great equations to tell, which is called wave function. The wave function tells us that the density of the electron with the location. Okay, we call this probability. We cannot predict. It's not easy to tell the way the electron is, but it will be possible to predict or use the probability to find out where the electron is. Okay, so these are the three. This is the wave mechanics, and after that we talk about the electron energy state and electron configuration and stable configuration and valence electron. So for the first three topics, I think we all know that is you already know this. I think it's not difficult. So for the stable configuration, that means if you have S2P6, that's very stable, right? So in the end, we know that we want to find out that the electron configuration for the stable elements, which is S2P6. Okay, and then valence electrons. Valence electron is the definition of the valence electron is the outermost shell, the electrons in the outermost shell. That's called valence electron. And this electron is very active. So when you think of this element, these 5 electrons are most active compared to the electrons in the inner shell of the atom, right? So these 5 electrons is active. So everything when the chemical reaction occurred, these 5 electrons participate the chemical reaction. Right, and then this is called modified d electron count method to know that valence electrons, the number of the valence electron in transition metal in this area, right? In this one, in this place. Okay. So today we are going to talk about the section 2.4 periodic table. In the beginning, let's think of the history of atom first. I hope you still remember Dalton. Dalton, he is the first one who created the atomic model, right? And we know that he described the model atomic. This atom is small, spherical, and indivisible. And there are 5 description of the Dalton model, and we know all. I have explained this for you before. So Dalton not only has a definition, Dalton not only defined the atoms, but also he also draw the atomic symbols. For example, he used symbols to represent elements. For example, this is hydrogen. He drew a picture like this, and I don't know what's this. This is carbon, oxygen. phosphorus, sulfur. So all the elements has different symbols, and also this is at that time they call weight, and now you know this atomic number, right? Atomic number. So Dalton devised the first atom symbols, but they looks a little bit different from the one we use today. For example, like this. We don't know why it's this, right? So not only he described the atoms, but he also put the atom together and become molecular. But at that time, we don't have the word called molecular. They call binary. So this is single, right? And this is only one atoms. So you have binary. You put two atoms together. For example, you put the number 1 hydrogen and number 4 here together, and you become this one. Okay, and not only this is binary. This is ternary. Ternary is 3, right? 4 is quaternary. Quaternary, you put 4 together, and 5, 6. So Dalton think that you can put two atoms together to become 2 atoms, 3 atoms, 4 atoms. And as we know now, these are called molecules, right? Okay, let's go to the history of periodical table. So once you know that we have atoms, and we put 2 atoms together, become molecules. So in the beginning of the periodical table, the first basic elements is from Aristotle. He thinks that there are 4 elements, basic elements. They are earth, fire, water, and air, right? So if you, and between air and fire is hot, water and air is wet, right? Water and earth is cold, and earth and fire is dry, something like this. And after that, after decades, centuries ago, later, this is in 1789. This is Lavoisier. He published a list of 33 chemical elements. So at that time, we already know there are 33 elements. And he thinks that these 33 elements can be grouped into gases, metal, non-metal, and earth. So he put these 33 into this 1, 2, 3, 4 categories. And he's the father of modern chemistry. So with the time going by, and then we will find more elements, right? So in 1829, this gentleman, Daubreuil, observed that many of the elements could be grouped into triad. Triad means that you have many elements. You put 3 into one group. Like for example, group A, there are 3 elements. Group B, there are 3 elements. Group C, there are 3 elements. At that time, he based on the chemical properties. For example, he put lithium, sodium, and potassium together, or grouped it together as a being soft, reactive, and metals. So as we know now, lithium, sodium, potassium, they are soft and very reactive because they have only one valence electron, right? And very reactive metals. He's right. But is there any better way to group it? So Daubreuil also observed that when arranged by atom weight, the second numbers of each triad was roughly the average of the first and the third. So he thinks that the sodium will between the property of the sodium will between the lithium and potassium. So this became known as a law of triads. And this gentleman, he put 8 together. Instead of 3, he put 8 together. So this is called laws of additive. John Newlands. So English chemist John Newlands published a series of papers in 1864 and 1865 that describe his attempts at classifying the elements. So he thinks that, well, it looks like music. Now, if you put 8 together, that'll be helium, hydrogen, lithium, barium, boron, carbon, nitrogen, oxygen, and this is one group. and fluoride will be the next. Okay, it sounds very interesting, right? Although we don't think it's correct, is very is 100% right. It's not. So when listed in order of the increasing atomic weight, the similar physical and chemical properties recurred at intervals of 8. So you put 8 together, and then which he likened to octave of music. So octave of music is like looks like music, right? So the law of the octave, however, was ridiculous by his counterparts theories. Okay. Right, this is true now. This is called Mendeleev periodic table. Mendeleev is a great man. He is the best known for creating periodic table of elements in 1869. So at that time, he found this is the element he found. The scientists found at that time, and then he grouped this like this kind of table. But there are some of the element missing. At that time, it hadn't discovered it yet. So they left the spaces for the elements he predicted, and also predict the property of these elements by using patterns he found in other elements. So the great thing for this periodic table is that he put these elements together in this order, and there are some of the element hasn't discovered it yet at that time, but he can predict the property of these elements according to this periodic table. For example, here you have 3 valence electrons. Okay, and here you will have 4 valence electrons. That's he can predict, but we don't know who. We haven't at that time. They haven't found out what is this, but they already can predict the property. That's how great he is. Instead, apart from Mendeleev from Russia, and this guy from a German chemist, he called Mayer. He also found this periodic table almost at the same time. But Mendeleev is the first one announced, so we remember him most. But however, for Mayer, for the periodic table, we also need to give him a credit because he's also the one who found this table. So this is the table we know now. And then we understand all of the elements in this periodic table. I'm sure you all know this. I think when you are in junior high school, you need to remember all of this, right? So from the lithium, barium, boron, carbon, nitrogen, oxygen, fluorine, neon, and blah, blah, blah. You all need to remember. I hope. Am I correct? Am I right? Right? Junior high, right? Junior high school. Right, okay. So, and of course, we give some numbers to represent some property in the periodic table in this box. For example, this is 29 is atomic number, and this 63.54 is atomic weight. So, but however, you can put different numbers to represent different properties. Okay, and this is simple periodic table tells us that if there's no color in this box, it represents metal. So you know that most of the elements in the periodic table are metals. Okay, and this is non-metal, only this part, small portion. And this is intermediate, that means what? Semiconductor. Okay, and then you know this is called alkaline earth metal. This is alkaline earth metal, and this inner gases. This is halogens. So now there are many type of the periodic table, and you can have some different properties here. So this is the table. The current standard table contains 118 elements today. So this element we can find so far 118 elements. And from uranium here, this is synthetic elements. We can synthesize the different element by what? By put the proton into the atom, right? So you can create different, you can create new elements, but they are all very radiative, sorry. Okay, so now let's introduce the periodic table one by column by column. Okay, the first column is called also this is called alkaline element. Alkaline metals is in the group 1. Okay, it's lithium, sodium, potassium, okay, etc., etc. Okay, and it's very reactive, malleable, ductile, and good conductor. So most reactive elements are cesium and francium. The cesium is here and francium is here. Why? Why they are very reactive? Because the electron is very far away from the neutron, from the nucleus, right? So the electron is easier to move away from the element, from atoms. That's why it's very reactive, right? And can explode when exposed to the water. This is, if you put it to water, it's just explode, and very reactive, very heavily. So one loosened bound valence electron. So this only one electron, which is very easy to get loose, run away from the atom. The second column is alkaline earth metal. The alkaline earth metal, also known as a group 2A here. Okay, the low electron affinities and the electron negativities. And we are going to talk about electron negativity later. Of course, you know there are two valence electrons, two electrons in the outer shell here. And the small atomic radius than alkali metals. The atom, this one will be smaller than this one. Why? We know this is n equal, for the quantum number, this is n equal to 1, right? N2, n equal to 3, 4, 5. When we talk about principal quantum number, we talk about the size. So the size, this one will be smaller than this one. This one will be smaller than this one. So the size will be increased. So how about this? When we talk about the same size, when we talk about the same principal quantum number, like for example, the quantum number 2, and while the barium, the size of barium will be smaller than the size of the lithium. Think of that, and we are going to talk about this later. Okay, this is important. Okay, radiation divalence cation. So if you lose 2 electrons, this element will become cation, right? Lose 2 electrons. However, if you gain 1 electron, you will become anion, right? Okay, and then next is the transition metal. Yeah, this is our cold transition metal. Very unreactive, malleable. Compared to these two groups, these are more unreactive. Okay, and then high melting and boiling points. What does that mean? High melting and boiling points. They are is present as a form of solid, right? That's why if you increase the temperature, it's difficult to become liquid or difficult to become gas. Okay, the third point is inhibit wide range of the oxidation states. So because you have more than 2 valence electrons, you can have 3, 4, 5, 6 valence electrons. So you will have a wide range of the oxidation states and low ionization energy. Okay, when we finish this transition metal, let's think of these noble gases, or we call inner gas. Noble gases is non-reactive because we know that it's S2P6, right? The complete valence shell, complete the valence shell is all the electron is all stable and fixed, tight in the atom, and very low electronegativity. We'll talk about electronegativity very soon. Okay, electronegativity means that you can think of, does this element likes electron or not? If this element like electron, the negativity will be high. If the this element doesn't like electron, then electronegativity will be low. Okay. And also the low boiling points. What does that mean? Low boiling point means that if we increase the temperature a little bit, it will become what? The element will become gas. Okay. For example, helium, the boiling point is very low. Okay. If you reduce temperature to 0 Kelvin, what helium will be? A. For example, if you decrease the temperature to 0 Kelvin, what helium will be? In the form of A, gas, B, liquid, C, solid, D, none of above. Which one? If you decrease the temperature to 0 Kelvin, helium will become gas, liquid, or solid, or none of them. Which one? Raise your hand, 0.5. You have nothing to lose if you guess it wrong. Yes, please. Huh? D, none of this. I'm sorry, it's not correct answer. Yes. Yes, please. Solid, right? Thank you. You can solid. You can solid. Okay. So it will stay there. It won't move. We are going to talk about this 0 Kelvin temperature. So, but of course, in the room temperature, it's all in the gas form. But however, if we increase the temperature a little bit higher, it will become gas. So this is a discovery of inner gases. Okay, these two gentlemen, they all get Nobel Prize because of the discovery of inner gas. Please read this by yourself. Next one is called halogens. Halogens is this one: fluorine, chlorine, bromine, iodine, and what's this? Okay, okay. So 7 valence electrons here. So you have 7 valence electrons. So what you need is extra 1 electron to get S2P6. That means what? These elements likes electron very, very much. So they have a very high electron negativity. And they are very reactive with these two groups, these two columns. Okay? And very low ionization energy. Easy to take electron away too, because you have a lot of electrons. Okay, and then next one we want to introduce is lanthanide, the group of lanthanide here, this part. The group of lanthanide is a silver white metals that tarnish when exposed to the air and very reactive. Okay, lanthanide. And high melting and boiling points, that means what? It's in the form of solid in the room temperature. Okay, and then strong reducing agent. It is a good reducing agent, very reactive. And next group here, this is lanthanide, right? And this is called actinide. Actinide is that all radioactive materials. Okay, you don't like this that much. Okay, highly electron positive and very dense metal. Very dense metal means what? Very heavy. Why? Because you have a lot in this area, element in this region, you have a lot of proton and a lot of neutron. That's why it's very heavy, right? Okay. Right. Just for your information, for this lanthanide group is very, very important for semiconductor or for very high-tech applications. So it's very important to have these metals. And these metals are mainly in mainland China. So there's many applications to use these elements. Okay, but how to get these elements? How to get pure of these elements? It's in China, right? They use very strong acid because they all this kind of material is all hide in earth. So you take this earth away and pour a very strong acid into this earth, and then this one will be melt, become liquid and come out. So you just extract the metals. So you got a lot heavy pollutions for the earth. And what happened to the earth? Just leave it. Right? So all the life die because you put a heavy strong acid into this land. So that land cannot be used anymore. In order to get these very precious metal elements, that's the way they do it. Okay, so now let's go to the important part. We want to talk about the periodical table today. It's called Trends of the Periods. So can you find any rules according to this periodical table? So the trace of the periods is that element in this same periods show the trend in there are 4 topics we want to talk. The first one is called atomic radius. Is any rules we can follow according to this periodic table? First, atomic radius. The second one is called electronegativity. That's what we talked previously about 5 minutes ago. The third one is electron affinity. The fourth one is ionization energy. So these 4 topics are the things we want to know according to the periodic table. Okay, let's move to the first topic. This is the table showing. This is the figure showing you that in x-axis this atomic number from 1, 2, 3, 4 until 90, and 1 is 1. The atomic number 1 is what? Is hydrogen, right? 2 is helium. 3 is lithium, right? Okay, and then the y-axis is the size, is angstroms. So as you can see, from 1, 2, 3, 4, 5, 6 until 10, and then increase, decrease, increase, decrease, increase, decrease, increase. Okay, is any rules we can follow? So this is the size of the atoms. Okay, and as you can see, this is 1A group in the periodical table, 2A, 3A. You have transition metal missing here. We don't talk about this now. Okay, 3A, 4A, 5A, 6, 7A. And the number here is, the unit of the number here is called picometer. Pico is very small, it's 10 to 12 meter. Nanometer is 10 to minus 9, right? Meter. And this is 10 to minus 12 meter. You don't need to remember this. I don't want you to remember this, the size of this, but I want you to see physically, as you can see, when you increase the principal quantum number from 1, 2, 3, 4, 5, 6, what can you see? The size of the atom increased, right? So increasing the atomic radius, the size of the atom increased. Why? Because the principal quantum number told you that if you increase the principal quantum number from 1 to 3 to 4, the size will increase. So N1, N2, N3, N4. And how about this one? You have the same principal quantum number. And this is called 1. You only have 1 electrons, right, in s orbital. And you have 2 electrons in s orbital. So S1, S2, P1, P2, P3, P4, P5, P6. What can you see? the size of the atom decreased. The size of atom decreased mainly. So why? You know why? That's because that when you have lithium, how many protons inside the atom? 3, right? You have 4, 5, 6, 7. So that means when you have more protons, you have more positive charge. And you have electron will be what? Will be pulled into these atoms. Why? Because Coulombic attraction. You have negative electron, you have positive electrons. So you have negative electron, you have positive proton. And then they will attract each other. So the electron will be pulled into this to become closer to the nucleus in this atom. That's why the size will decrease. So you have more proton number, you have more protons, the size will decrease. Okay? So on Friday, this might be the Kahoot. The question of the Kahoot, I want you to get the right answer, okay? So when you visit Google, the website of Google, and you type the atomic radius, and you find the picture, this is the picture showing you like something like this. But again, I don't want you to remember the size of this radius. I just want you to remember the traits. If you increase the principal quantum number, you will increase the atomic radius. If you increase the atomic number in the same principal quantum number, and then the atomic radius will decrease. Okay, this is first one. Are you with me so far? This is important. So this gives you a roughly idea. You want to compare the size. For example, I want you to compare the size of lithium, carbon, and fluorine. Can you compare the size for me? You will say that, well, the size of lithium atom will be bigger than the carbon and will be bigger than the fluorine. Okay. Okay. If in Kahoot, the question in Kahoot is that please compare the size of the potassium, sodium, and lithium. Can you tell me this? Yes, right. The size of potassium will be bigger than the size of the sodium will be bigger than the size of lithium. And give me the answer. Give me why. Give me the answer of why. Okay. Okay, so the next topic is electron negativity. So electron negativity, we use a symbol called chi. Chi. Sometimes you call it X, or it's Greek letter, so we call it chi. Chi. It's a chemical properties that describe the tendency of an atom or a functional groups to attract electrons. So attract electron means what? Means how much you like electrons. If you like electron, your electron negativity value will be high. Okay. So an atom's electron negativity is affected by both its atomic number and its distance, at which its valence electrons recedes from the charged nucleus. So the higher the associated electron negativity number, the more elements of the or compounds attract electrons toward it. Right. So this is, before we really talk about the electron negativity, let's take a look of the cation and anion. The cation and anion is that the column is similar valence structure, right? As we know that the column here, the column 1, column 2, this one has similar valence structure. That means what? The valence electron is 1, number of valence electron is 1, number of valence electron is 2, right? So it is easy to give up 1 electron, and this one easy to give up 2 electrons. How about this level? Fluorine, chlorine, bromine. This one is inner gases, and this one is accept 1 electron, and this one is accept 2 electrons. So for this part, we call this electropositive elements. And electropositive element means that ready to give up electrons to become cation. So this part is to give up electrons and become cation, and this part is to receive, to acquire electrons, and to become minus electron negative elements. We call anion. Okay, anion. So positive element and the negative elements. Right, so when we think of electron negativity, we need to think of positive anion, electropositive element and electron negative elements. So this is this is periodical table. The number showing you here is the electron negativity, the value of electron negativity. This kind of index is like temperature. Temperature 25. What does temperature 25 tell us? It can be Celsius, right? It can be Fahrenheit. Okay, so temperature can be Fahrenheit or Celsius, but does it have physical meaning? No. But this kind of number is kind of index. It's kind of index telling you that if the index is high, that means this element likes electrons. The same as temperature. If temperature is high, that means it's hot, right? If temperature cold, then it's cold. If the temperature is low, then it's cold. So electron negativity increases from left to the right. So please remember this. From the left to the right, electron negativity increase. As you can see, this is 1.0, 1.5, 2.0, 2.5 increase. Why? Because this one is electropositive element. So it's easy to release 1 electrons. And this one is easy to receive 1 electron. So this one, number 4, it means what? This number 4 means you like electrons. Okay? And this is this transition metal is always in between of 2 to 1, 1.3, 1.5, 1.9, something like this. And there's no number for inner gases. As you can see, it's very stable. You don't like electron, you don't hate electron. Okay, so this, as you can see, the electron negativity, value of electron negativity increase from the left to the right, increase from the top to the decrease from the top to the bottom, and lowest is 0.7, right? Why? Because this one is easier to lose 1 electrons compared to this part. There's only one exception, which is hydrogen. There's no location for hydrogen in periodical table. It should be somewhere here, right? Okay, this is exceptional case. So the Francis is very low, which is 0.7, which is lowest. The highest is is this one, fluoride. Okay, so this is the topic of the electron negativity. Right, and before we move to another topic, the next topic, let's play Kahoot now. Refresh ourselves first. You know, we just have a quick learn about two topics. The first one is atomic radius. Okay, according to the periodical table, you know the traits. The second one is called electronegativity, and you also know the traits. And the third one is called electron affinity. What is electron affinity? Electron affinity is that in chemistry and atom physics, the electron affinity of the atom or molecules is defined as the amount of energy released or spent. You know, you can release the heat, you can gain the energy, you can release the energy, right? And then when the electron is added to a neutral atoms or molecules in a gaseous state, why gaseous state? Because it doesn't want to be influenced by neighbor adjacent atoms. Okay, in a gaseous state to form a negative ion. The chemical formula looks like this. So you have a neutral element, and you will gain the electrons, and you become an ion, no matter you like it or not. Okay, and then you will have energy. It can be released energy, or it can be received energy. So this is a trait look like this. Electron affinities as a Vs, the atomic number. As you can see, the trait like this. Right. So this is the energy, and as you can see, this part is high. Why? The fluorine, chlorine, boron, iodine is high. Why? Because this is easy to receive an electron. Right? And why lithium, sodium, Kelvin is low? Why? This is easier to kick away over one electron. Okay, so this is the traits. Again, I don't want you to remember the numbers. I just want you to remember, is this element easy to gain electron or easy to release an electron? Okay, the topic 4 is the ionization energy. This is also important. The ionization energy tells us that you already learned this before. Is a quantitatively defined as the amount of the energy required to remove the most losing bound electrons, the valence electrons of the isolated gaseous atoms to form a cation. So in the previous topic, we want to force electron into this atom. This is called affinity. And for the ionization energy is that I want to give this element energy and want to release one electron. So this is called ionization energy. So this is opposite of the electron affinity. So where X is an atom or molecules capable of being ionized. So this X cation is that atom or molecules with the electron moved, and the electron is the moved electron. So you want to take electron 1 away from this atom, and the energy you require is called ionization energy. So you compare to electron affinity, is like this. You have element X, and then this you get electron, you get energy, and then you release one electron. And this is you force to give X one electron, and you release or you gain energy. And it become what? This become an ion. This become cation. So I hope you still remember we have a term called first ionization energy. What is first ionization energy? For example, this element is neutral. There's no charge, no matter negative charge or positive charge. And then you take the first electron away, the energy you gain or you lose is called first ionization energy. So normally you need to give the energy to this electron, to this element. Okay, so this is called first ionization energy. And in your midterm exam, this figure might show in your midterm exam. Okay, so please remember this. Okay, so let's say, so if I ask you to rank the first ionization energy of the helium, neon, and argon, can you rank the first ionization energy for me and why? That's the answer I want you to tell me in your midterm exam. But don't worry about this now, I'm going to tell you. So first ionization energy is that you take the first electron away from the atom. This is called first, the energy required is called first ionization energy. Right, so this x-axis is the atomic number from 1, 2, 3, 4, 5, 6, 20. Okay, actually, you cannot link the line between 1 to 2. Do you know why? Do you know why? There's no line between 1 and 2. Why? It doesn't make sense. There's no point which is 1.5, right? Because the quantum atomic number is quantized. There's no 1.5, so you cannot link these two together. But anyway, this is from our textbook. Understand? Right? This is quantized. There's no line here. You cannot draw a line here. Okay. Anyway, so the y-axis is the energy required to move one electron away from this atom. So this is the unit of this energy is kilojoule per mole. I'm sure you don't familiar with this number. So I want to make it easier for you. We use electron volt. Electron volt. And if you have 500 kilojoule per mole energy, and you use this to convert to become it become 5.2 electron volt, and this is 10.4 electron volt, 15.6 electron volt, etc. Okay, so does anybody want to tell me what is this? What is the ionization energy of the hydrogen? Yes, please. Okay, 13.6, right? Why? Because it is the value of K. Remember, when we learn about atomic number, the Bohr atomic model, we have three numbers we need to remember. The first one is radius, right? A0, right? Which is 5.3 Armstrong, right? The second one is K, right? It's 13.6 electron volt. The number three is velocity, which is 1% of the speed of the light. We call V1. Remember, these three important numbers you need to remember. So for Bohr atomic model, this ionization energy will be what? 13.6 electron volt. Because you only have one photon and one electron, and you want to take this away, the energy required is called first ionization energy. Okay, however, for helium, you have two protons, and you have two electrons. And the first electron you need to move away, and this is also called first ionization energy. And as you can see, this energy is high. If you want to remove this electron away, the energy is higher than this electron. Why? Because the radius is small. Remember, when we talk about atomic radius, the size of atom, this one is helium, is smaller than hydrogen. Why? Because I have two electrons, or I have two protons, and this two proton is positive charged. So electron will be pulled in, will be closer to this proton. And then if this electron is closer to this, you know the size, this is bigger size, this small size, right? If the electron want to move away, then you need more energy to take this electron away from this atom. That's why the energy required is high. Does it make sense to you? Are you with me so far? Yes, right. So this is called 1s. So 1s1, 1s2. How about lithium? Lithium is the quantum number is 2, right? So the size is bigger. The size is bigger. So if you think of the hydrogen and lithium, the size is bigger, so the energy will be low. So this electron is far away from the center of this nucleus. So energy lithium will be low. The first electron, right? Okay. So this is 2s. The same 1s, 2s, 2s1, 2s2. And then energy increase. Why? Because this is the same. Again, 3, 4, and 2p. The electron, the number of photon increase, but the size of atom decrease. So the reason you want to take away electron is difficult. That's why energy is increased. So the same energy level, for example, 2p, but more proton, right? So the size reduce, the size of size of the atom reduce. So electron has more Coulombic attraction between each other. So electron is more bound with the atom. And if you want to take out, you need more energy. So energy increase. So in your midterm exam or in Kahoot, if I want you to rank the first ionization energy of lithium, carbon, and fluoride, can you tell me which one require more energy? Fluoride, larger than carbon, larger than lithium, right? And tell me the answer. Tell me why. Give me this sentence. Okay? In your midterm exam or in the Kahoot next week. So the same as 3s and 3p. 4s, 4p. That's the same trace. You might ask me, Professor, why the ionization energy of barium is larger than the boron. Well, it's a little bit complicated. We don't talk about this now. But you just know the general traits. Okay. So there are two things you want to compare. One is the same principal quantum number, 1, 2, 3, and also the different principal quantum number, 1, 2, 3. Why? Why the first ionization energy potassium is smaller than sodium, smaller than lithium, and smaller than hydrogen? Why? Because electron is far away from the nucleus. This is very far. The first electron in the 4s is very far from the nucleus. But because of the screen effect, you have 3s, 2s, and 1s electrons in the potassium. So that's why this electron is easier to move out. The first electron is easier to move out from the atom. Okay, and the same story as S2, right? This S1, this S2. And also, when you think of the inner gases, that's the same. That's because of the screen effect. Or you can say that the size of the atom is larger. So the valence shell, the electron in the valence shell, the electron is easier to move out because that's called first ionization. The first one move out is called first ionization energy. Okay. So this is the first ionization energy versus the atomic number here from this and this. Now this it makes sense to you, right? They don't link the line together because it doesn't mean anything if you put a line between these 2 points. So here is that it's called photon electron spectroscopy. We call PES. How are you going to measure the ionization energy, especially first ionization energy? That's what this tool we use, and this tool we still use to find out the bonding, the bonds. Okay, to measure the ionization energy, it's called bonding energy. So we have atom beams into this chamber. So it should be gas. It should be gas. So we put an unknown atom into this chamber, and we shoot the photons into this chamber. You can use laser, for example. Okay. And again, for example, this is the atom, and there's a bonding energy of these electrons to this atom. And because we use photon to hit this atom, and if the energy of photon is high enough, one of the electron will be moved out, right? So when we move out, we call scattered or free electrons. This is photon, right? Energy high enough, electron will be moved out. For example, hydrogen will be 13.6 electron volt. Okay, so electron move out, and this is called photoelectrons. So electron move out, electron come out from this atom, and electron can be ejected from this chamber. So these photoelectrons. So we all know that electron got negative charge. So we can analyze the energy of the electrons. So if you have slow electron and you have fast electron and you got the right energy, you can get the right electron with the right energy will hit the detector. So by tuning the electrostatic analyzer, by tuning the magnetic wave, the field of the electron magnetic wave, we'll be able to detect the energy of the photoelectron. So once we know the energy of this free electron, we call photoelectron, then we can have an equation like this. Matter energy interaction. I hope you still remember. And we got electron, photoelectron, right? So we have instant energy, and we have kinetic energy plus what? Binding energy. This is potential energy. So according to the energy conservation, we can put this equation, and we know the instant energy of the photon, and we can measure the kinetic energy because of what? Because of this. Because we can get the kinetic energy of this. So that's why, according to energy conservation, we got this number, then we know this number. Okay, it's set by experiment, and we got this energy measured by detectors. So we know the bonding energy, unique to identity. So the important thing is that if we have an unknown element, we put this unknown element into this chamber, and we give the energy to this atom, and we get the photoelectron out, and we measure the energy of these photoelectrons, and we will be able to know the bonding energy. And this is called, there are two tools. The PES can divide it into two. One is use X-ray as the source of the energy. One is use the ultraviolet light as a as the energy. So if you use X-ray, the range of X-ray is about 1 angstrom. And if you use ultraviolet, that will be 100 angstrom. The machine looks like this, expensive. And what kind of information you can get? The information you can get is this. You know the electron in 2p orbital and electron in 2s orbitals. electron 3ps orbital and electron in a 3d orbital, it looks like this. This kinetic energy and intensities. So this is the, you can identify the where is electron came from and what kind of element is this. So this is called chemical analysis. We can measure the binding energy of the electrons in individual elements. For example, this energy, this 2p energy is from, for example, like 550, for example. It can be a certain, it should be a certain element. For example, A element, 2p is here, but B element 2p will be here. It won't be the same. It won't be the same energy, kinetic energy, right? Because the radius is different. Okay, so this is called chemical analysis. So once you got this spectrum, you can tell what kind of element you measure, and you can tell the energy of 2p, energy of 2s, 3p, 3s, and 3d. So again, with the unknown material, you got a set of line. And you can also know the bonding energy if you have molecular into this chamber. So SPS is a very powerful tools for you to analyze the bonding energy. Okay? So you have multi-electrons from a single species. Multi-electrons, right? S2s, 2p, and 3s, 3p, multi-elements. Okay, so this is also the topic I want you to know, and this might be the topic, might be your midterm exam. This question might show up in your midterm exam paper. It's called ionization energy. I want you to rank this. For example, this is the relative number of electrons: hydrogen, helium, lithium, barium, and boron. And this is the energy. Again, it's megajoule per mole. And this is called characteristic energy. For example, hydrogen, the energy should be here. Helium should be here. So if you convert this megajoule per mole energy unit to become electron volt, and that will be, hydrogen will be 13.6 electron volt, right? And helium will be increased. So this is 1s electrons. 1s electrons, helium has 2 electrons. Hydrogen has 1 electron in 1s orbital. And helium has 2, and why helium, the ionization energy of helium increase because the energy from low to high. And why? More proton, tighter bondings. So the energy will be high. Lithium will be high. And barium will be high, very high. 1s electrons. How about 2s? Lithium has 2 electrons in 1s orbital and 1 electron in 2s orbital. Right? And barium has 2 electrons in the orbitals. Again, so the energy looks like this. The explanation is more protons and tighter bonding. And 2p is less, energy is less. And as you can see, this is outer electron in the outer shell, inner shell. So the energy of electron is increasing heavily. It's 13.6 megajoule per mole. So the explanation is ionization energy of the electron in shell M, N is equal to 2, and P, right? It's much lower than that in K shell. Why? The energy here is higher than energy here if you want to take out. The ionization energy in this shell is higher than the ionization energy of the electron in this shell. And then for the case of boron, the intensity of 2p This is intensity, okay? This is intensity. Intensity of 2p, 1 electron, is about half of 2s, because 2s has 2 electrons. So the intensity is about half. So this is about double. Intensity is about double compared to this one. Right.